fact I learned this week?
What?
The 60 minutes in 1 hour and 60 seconds in 1 minute originated from ancient Babylon.
Interesting.
How far back it all came. They realized it's easily divisible by whole numbers. That's how we have our time frame.
Interesting. Huh. Yeah, it's so interesting that like a lot of these things they just like kind of decided just like long ago, somewhat arbitrarily, and then now it's just our custom for a lot of things.
That's the thing. It wasn't necessarily arbitrarily. It was just a very convenient number to split up according to how based on why they chose it.
I see.
And so it was. It's just fascinating. Like you said, because we look back and we just don't think much of it. And sometimes people, I know in conversation and in modern science, even we'll talk about previous people groups from however many thousands of years ago and say that they're much dumb. To see the science that came out of it, to see the little things that are still in use today, it's interesting.
Yeah, no, for sure. All right, it's 4 o'clock, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Great.
Hanging in there. One more day, spring break right around the corner. Hopefully everyone's excited. I'm excited. Okay, so plan for today is to finish up our lecture note on Fourier series. So I think we should be able to finish. So by the time we end class today, you should have everything you need to do homework 5. So remember, homework 5 is out there, but I don't expect you guys to work on it over spring break. I want you guys just to rest. It's just with the timing of everything, I just had to assign it out there. But it's not going to be due until the Friday after we come back from spring break. So you'll have time to do it when. Okay. All right, and so that's the plan for today. Any questions I can answer before we get started? Okay, all right, so let's go ahead and get rolling. Okay, so last time we were here on Tuesday, we introduced this idea of the Fourier series expansion as a way to represent any periodic function. Okay. Right. And so what we says that any function f of t, where the only requirement for f of t is that it be a periodic function. right, is equal to A naught plus summation from n is equal to 1 to infinity of an cosine of nt plus b sine of n times t. Okay. Bn. Right? Where the goal of these types of problems or the goals of these types of expansions is to compute the values of the coefficients. Okay. Where the coefficients are a0, an, and b. So the last example that we did on Tuesday, we did just that, right? So we took a periodic function, a fairly simple periodic function, and we computed its corresponding Fourier series coefficients. Okay. Now I did forget to talk about one specific topic last time, or we kind of touched on it, but we didn't really kind of dive too much into its applications, which is the issue of truncation, right? And so what we said last time is that normally if you're going to be computing the full expansion, right? Right, technically this is an infinite summation. Right, and so in order to compute the true expansion, you have to keep computing terms up into infinity. Which obviously is not possible. Right? And so the way that we address this, or the way that we make the Fourier series more practical, is we truncate the series. Right. So we basically set an upper limit where we said that we're only going to compute the first 10 terms, or the first 5 terms of the expansion, right? And then we compute just those terms. So there's a lot of practical applications for truncation as well. Right. So before I kind of we move forward, I want to make sure we mention that, just because last time was kind of more heavy on just the math stuff, right? So the most obvious or the most commonly used application for truncation is in signal filtering. In particular, filtering out the noise in a signal. So if you've ever looked at kind of a an electric signal, whether I think the most obvious one would be kind of like a sound signal, right? There's always a little bit of noise that's right. So noise being defined as a kind of a very high frequency kind of sound that kind of oscillates back and forth. Right? And so if you have a typical signal, right, something like this, right, you might have a noisy signal where the plot kind of looks a little bit fuzzy like this, right? Right. So underneath the noise, you may see a general pattern, right? So you can see here this kind of looks like a sine wave, but because of the noise, it's kind of oscillating up and back and forth, just like that. Okay. Now, generally, when you're analyzing signals, when you're using them for engineering applications, noise is not it's not preferred, right? We would ideally like to have a signal without the noise. And so what happens typically, and this happens automatically a lot nowadays, and you'd be surprised, just in very basic just audio processing, just sending your voice signal from one location to another, there's a lot of filters that are done. Okay. One example of a filter, probably the first filter that I think most people learn when they're going through signal processing is what's known as a low pass filter. So that might be a term that you've heard kind of before in the past, right? So a low pass filter is one which only allows lower value frequencies to pass through the filter. Any frequency that's higher than a specific threshold gets filtered out. So this is beneficial for noise filtering because noise almost always is extremely high frequency. Noise almost never occurs in kind of a low frequency. And so by eliminating these high frequency components, we can get a signal that's often much smoother and much more easy to analyze. Okay. So how do we achieve a low pass filter? Well, right, remember what we said before, that the higher order Fourier coefficients, so the ones that are, where n is equal to 10, 20, 30, right? These are all high frequency contributions, right? Because as n increases, right, the frequency of the sine or cosine term that it's associated with also increases as well, right? And so by truncating our signal, right, so only keeping the first, few low numbered coefficients, we're effectively performing a low pass filter. So I wanted to kind of emphasize and kind of make that very clear that when we're truncating a Fourier series series expansion, right, we're really just eliminating all the high frequency or all the really high frequency components of the signal, right? And there are actually real engineering applications to that. Okay, besides the fact just making the problem just more practical, there are benefits to doing so as well. All right. Now you do have to be careful though, because sometimes a lot of times when you want to filter out the noise, you sometimes accidentally filter out some important features of the signal as well. And so you do have to be a little bit careful in terms of how much you discard or where you truncate, because you want to make sure that you get enough of the signal's character still maintained after the. Okay. And that's something that it's very application dependent. So there's not much more I can kind of really say beyond that, just talking in a general sense. But that is a factor consideration when you're doing these. Okay, any questions on noise filtering? All right, another kind of a cool application for truncation has to do with actually audiophile sizes. And so if you've ever, I'm going to probably everyone in this room has done so, right? So let's say that you've downloaded an MP3 file or you downloaded an audio file of a song, right? There's usually a difference compared to, if you just took, let's say an audio recording, let's say you just ripped it straight from YouTube, right? That file is probably going to be fairly small, right? But if you took like a very high quality recording of let's say a symphony orchestra, those files will be much larger, right? And I think, just qualitatively, you can tell just by listening to it that, generally the more space or the more memory an audio file takes up, the higher quality sound that's going to come out, right?
That translates to the amount of waves essentially that are in that file.
Exactly, right, right. So when you do audio file processing, like you're processing kind of an audio signal and kind of encoding it into a computer file, right? Essentially, what part of that process is taking a Fourier series expansion or Fourier series approximation of that signal. And the higher quality files will retain much more of those frequencies, which kind of results in a higher quality sound if you actually listen to it. Okay. Now you can listen to it, but that's part of the science that kind of goes into it. it's not everything that goes into it. It's audio compression is a very complex field itself. There's a lot of very highly developed tools, but that's kind of that's one of the driving kind of factors that goes. Okay. So this is kind of the logic behind audio compression. Okay. So how many Fourier terms, or just how many frequencies that you choose to maintain in your audio file will kind of determine the size of your file, but also determine the quality of sound you actually hear. Because the more frequencies that you retain, the deeper and more beautiful of the audio file that kind of results from. Okay, so I wanted to make sure I mentioned that just because it's those are very important applications that we're covering. Because I think with Fourier series, it's kind of one of those things also where it's very easy to get caught up in just computing the coefficients and just kind of doing it robotically. But it's always good to think about how these are actually applied. All right, any questions on that? Okay. All right, so let's go ahead and move on then. So, so far, if we look at the Fourier series up here, right, we've been able to apply this to periodic signals that have a period of 2 pi, right? Right? Which is very limiting, of course. There are, literally infinitely many periodic signals that have a period other than 2 pi. And so we need to basically take our Fourier series expansion here and generalize it to an arbitrary period. Okay. So it's not that much of an adjustment, and the coefficient calculations are very similar. There's just an extra factor for the period there, right? So the expansion with an arbitrary period looks like the following. So we have f of t is equal to a naught plus summation n is equal to 1 to infinity, right? Of an cosine, right? So far it looks the same. Now the only difference here is that inside the parentheses here, we need to add a factor that accounts for the new period, right? So now inside the parentheses, we have n pi times t divided by L, right? And I'll define L in a second, plus Bn sine of n pi t divided by L. Okay. Where L, right? L here is what we define as the half period. Emphasis on half, right? So I think one point of confusion for people is that when they're applying this formula here, they assume that L is the full period, but L is actually just the half period. So whatever your period is, just cut it in half. That is your L. Okay, and then the formulas for the coefficients also correspondingly change as well. So we have formulas for A naught. So A naught here is 1 divided by 2L, integral from minus L to L of f of t dt, right? So remember that is our mean value formula. Remember A0 is just the mean value of our function across one period. Next, we have the formula for an. So an is equal to 1 divided by L integral from minus L to L of f of t cosine of n pi t divided by L dt. Okay. And then Bn, very similarly, 1 divided by L integral from minus L to L f of t sine of n pi t divided by L dt. All right, but our procedure proceeds exactly the same. And so, we're going to do an example next, but you're going to see it's exactly the same as our, as the last example that we did on Tuesday. The only thing is just that, we have to factor in this additional factor of L. Okay, any questions on this before we jump into an example? Okay, all right, so let's go ahead and do an example. All right, so for this example, we are going to consider a sawtooth wave. Right? So we're going to say f of t, that's our periodic function. It's going to have a value of t, right? So it's going to be a linear function t from -1 is less than t is less than 1, okay? Okay, so let's plot this. Okay. So you have our plot, horizontal axis of t, vertical axis of f of t. Let's draw the bounds. And so we're going to go from -1 to 1. Okay. And then from -1 to 1, our periodic function here has a value of t. So that's just a straight line. Okay. So if we go down here, this is -1 up to 1, right? We can say that our periodic function looks like the following. Let me draw a straighter line. That kind of bugs me. And then since it's a periodic function, we assume that once it kind of reaches a full period, that this pattern is going to repeat itself. And so we reach up to 1, we come down. It's going to repeat like this. Same thing on the left-hand side. So, if you kind of draw this out for several periods, it looks like a sawtooth wave, hence the name sawtooth wave. Okay, so just like we did in the previous example, let's go ahead and compute the Fourier series coefficients, and we'll compute the first couple terms in the expansion. Let's just compute the first 3 terms. Okay. All right, so right away we can see here that the period of our function is not 2 pi. Our period here is actually 2. Right? Because from -1 to 1, that takes a time of 2, right? So that means our half period length of our L is going to be 1. Right? Half period is just the half of the Okay, so we're just basically going to take our three equations here, one for A0, one for AN, one for BN, and just kind of plug in our expression here and solve for that. Okay, any questions on the setup for the problem? Okay, all right, so let's go ahead and plug in and let's compute stuff. All right, so let's start with A0. So A0, that's our mean value formula. And so we have 1 divided by 2 times L, where L is just 1 in this case. Okay. Integral from -1 to 1 of T dt. All right, so this is a pretty simple integral. So let's go ahead and evaluate it. So this is 1/4 T squared, evaluated from -1 to 1. Okay. All right, so we get 1/4, 1 squared minus -1 squared. -1 squared is just 1. And so we have 1 minus 1, which is 0. So A naught in this case is equal to. Oops. My fat thumb ran across the screen. I apologize. Now it's gone. Come on. There we go. All right, so that makes sense, right? Because remember, A0 is represents the mean value of the formula across of the mean value of our function across that period, right? And so for a sawtooth wave, if we look at just one period, right? So we look at kind of this region right here, right? Our function starts at -1 and then it climbs gradually up to +1. And so you can see here, you can just kind of visually see that the average value of the function within this range should be 0. Because it spends an equal amount of time below the x-axis and equal amount of time above the x-axis. Okay, next let's compute an. So an, we're just going to plug in for our formula here. So what's 1 divided by L, which is 1, integral -1 to 1 of t cosine of n pi t divided by L, where L in this case is just 1. dt. All right. So we have a very classical integration by parts, right? And so we have to do that for this problem here. All right. So the first part of integration by parts, we're going to set equal to t, just because that one's going to differentiate out, right? So we take the derivative of t, we just get dt, right? And then for the other part, we're going to have the cosine there, so we have cosine of n pi t, right? The divide by L just kind of goes away just because L is 1 in this case, right? And so we take the antiderivative of that, we get 1 divided by n pi sine of n pi t. All right, so we go ahead and do our integration by parts. So we take this multiplied by this with a plus sign, and the integral of this multiplied by that with a minus sign, right? We get the following. So we get t divided by n pi sine of n pi t minus 1 over n pi integral sine of n pi t dt. Integrals from -1 to 1. All right, good. All right, so we do that last integral there. That one is straightforward because that one is just integral of sine, right? And so we do that, we get t over n pi sine of n pi t plus 1 over n pi squared cosine of n pi t, evaluated from t is equal to -1 to +1. All right, so let's go ahead and plug in our integration bounds, and then let's see what we get from here, right? So let's evaluate everything at t is equal to 1 first, right? And so we evaluate everything at t is equal to 1, we get 1 divided by n pi sine of n pi plus 1 over n pi squared cosine of n pi, okay, minus exact same result, just evaluate t at minus, right? So we have -1 over n pi sine of minus n pi plus 1 divided by n pi squared cosine of negative n pi. Okay. All right, so we have a lot of terms here, but you're going to see a lot of it's going to cancel out, and we're going to make use of the fact that we know that sine is an odd function, and we know that cosine is an even function, right? Right, because first thing we have here is sine of negative n pi, right? And so what do we know? Since sine is an odd function, right? So that means that sine of minus n pi is equal to minus sine of n pi, right? So the minus sign just kind of comes out in front just because of the symmetry of the odd functions that we have. Okay. And so what we get from that, this minus sign is going to cancel out with this minus sign. And so we get a positive 1 over n pi sine of n pi. Okay. And then because of the minus sign out in front of that parentheses, right, we have a positive 1 over n pi sine n pi on the first term, a negative 1 over n pi sine of n pi over there. And so these terms, this one here, are just going to cancel each other out. Okay. And then the other part here is that we have cosine of minus n pi here, right? We know that cosine is an even function. That means cosine of minus n pi is equal to cosine of n pi, right? So even functions, whatever you take for the argument, you just eliminate that minus. Okay, and so if you do that, that last term there then becomes 1 over n pi squared cosine of n pi, right? We still have the minus sign that comes out in front, right? So we have the minus sign that comes out from the integration. And so at the end, we have a minus 1 over n pi squared cosine of n pi, right? On the other term here, we have a positive 1 over n pi squared cosine n pi, right? So we have a positive version, a negative version here. And so those two are just going to cancel each other out. Okay? And so what we get in the end is an is equal to 0 for all n. Okay. Good. So just like our last example, we have a0 and an is equal to 0. All right, so you might be wondering, is it just a coincidence that the last two examples that we did, all the a coefficients are 0? Well, there's a reason for it, and actually, if you're kind of savvy, you can kind of look from the beginning of the problem, and you can kind of conclude right away that all the a coefficients will be 0. Okay, I'm just going to tease it for now. We'll kind of go over the exact reason later.
Cosine starts from 1, sine starts from 0, so that's cosine.
Doesn't have to do with that. It has to do with our original function, right? So if you look at our original function, it's a sawtooth wave, right? So there's actually some features of this wave that you kind of look at just right away, and you can kind of tell right away that the cosine or sine terms are going to be 0, right? It does have to do with the fact that sine is an odd function and cosine is an even function. So that'll be kind of the hint for that. So it's not exactly a coincidence that an is equal to 0 for this example and the previous example. Okay, but let's look at Bn, right? So let's just kind of continue with this problem as it is. So Bn, we're just going to plug into our formula once again. So we're going to have 1 divided by 1 integral minus 1 to 1 of t sine of n pi t divided by L, which is 1 dt. All right, so once again, we have a problem where we need to integrate by parts. And so I'm going to do that just kind of, we just saw it. So I'm just going to go fairly quickly here. So let's integrate by parts. Okay. And so we have u is equal to t, du is equal to dt. Okay, and then we have dv is equal to sine of n pi t, and then v is equal to minus 1 over n pi cosine of n pi t. Okay. All right, just like the previous example, we're going to take this one, multiply by that, add a plus sign. This one multiply by that, add a minus sign. Okay. And so we get minus t divided by n pi cosine of n pi t plus 1 over n pi integral cosine of n pi t minus 1 to 1. All right, so we performed that last integral there. That's just going to be integral of cosine of n pi t. That one's pretty straightforward to do, right? So we have minus t divided by n pi cosine of n pi t plus 1 divided by n pi squared sine of n pi t, okay? And we're going to evaluate this entire expression from minus 1 to 1. Okay, so let's go ahead and apply our integration bounds. And so just like before, we're going to have two terms here. Okay. So we plug in the integration bound at t is equal to 1. So we get minus 1 divided by n pi cosine of n pi plus 1 divided by n pi squared sine of n pi. Okay. Minus, exact same thing, evaluated at t is equal to minus 1. Okay. So then we have a, let's see. So we have the minus sign, then the t. So we have a positive 1 over n pi cosine of minus n pi, okay, plus 1 over n pi squared sine of minus n pi. Okay. So we better get something non-zero here because everything else has been zero so far. Okay, let's actually look at the sine terms first, right? So that's actually a term that we saw last time. And technically you could have done this in the previous part too. It's just, I wanted to show you that things cancel out, right? So here we have sine of n pi and sine of minus n pi, right? So what did we say about these specific terms last time, right? So since n is an integer, I guess it's n is a whole number. Right? The argument within the sign is always going to be some multiple of pi. So either pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, so on and so forth, right? And whenever you take the sign of some multiple of pi, you always get 0. Okay? So these terms are going to be 0. For sine right, so we can just eliminate those off the bat. Actually, in this case, they don't cancel. So we do need to eliminate it by the sign, by the sign. Okay. Okay. Other thing that we're going to apply here is going to remember that cosine is an even function. So this cosine of n pi becomes just a positive cosine of n pi. All right, and then so we have a -1 over n pi cosine n pi minus 1 over n pi cosine n pi. And so that what we get is Bn is equal to -2 over n pi cosine of n pi. All right, and so that is our solution there. And so, part of the problem is, so this is part one of the problem, right? We've come up with this expression for the coefficients. Now let's actually compute the first three coefficients here. Let's compute B1, B2, and B3. Okay, so B1, we're going to plug in n is equal to 1, so that is a minus 2 over pi. Cosine of pi, so cosine of pi is just -1, and so that minus sign is actually going to cancel out with that, right? And so for B1, we just get 2 over pi. All right, next we have B2. So B2, we're going to plug in n is equal to 2, so that's going to be 2 over 2 pi, and so that's going to be 1 over pi. Okay. Multiplied by cosine 2 pi. So cosine 2 pi is +1. And so that minus sign out in front is actually going to be retained. So we have a -1 over pi. And then for B3, so we plug in n is equal to 3, we get 2 over 3 pi, right? Cosine of 3 pi, so that we end up back on the negative x-axis again. So cosine 3 pi is -1. We have -1 times -1 is positive. Okay, so B3 is positive. Okay. And so if we plug these into our expansion, right, we get f of t is equal to, so first we have 2 over pi, and that is multiplied by sine of pi t, right, minus 1 over pi sine of 2 pi t plus 2 over 3 pi sine of 3 pi t. Okay, and of course this continues on forever. All right, so we've written the three terms. If we wanted to stop the expansion here and just say we only want the first three terms, we can say that we can truncate the expression. But that's not what the question asks. So the question asks to just compute the first three terms, and this will assume that there's more. Okay, so remember to kind of get this expression here, we're basically just plugging into our general Fourier series expansion, which is f of t is equal to a naught plus summation n is equal to 1 to infinity an cosine of n pi t divided by L plus bn sine of n pi t divided by L. Okay. Right. So we know that a0 and an are 0, and so we don't compute those terms. And then the next three terms that we compute are the first b terms, right? So b1, where n is equal to 1, b2, where n is equal to 2, and b3, where n is equal to 2. Okay, so that's how I got this kind of expression up here. Where we take these coefficients and we plug them into for bn. Okay. All right. Any questions on this so far? This example? Okay. Good. All right. So let's go back to the point that I had mentioned earlier, right? And so oftentimes when you're doing these Fourier series problems, you're going to run into situations where either the A coefficients are 0 or the B coefficients are 0, right? And so how can you tell, right? So is there a way to tell beforehand if, either A ends or B ends or 0? Because if you can, like that's going to save you a lot of work. because there's no need to compute something if you know ahead of time that's going to be 0. Okay. So the next section here is going to be simplifications. It does, yes.
So if it's symmetrical, you can automatically. That's yep, be in say symmetrical.
They're all symmetrical. It's just whichever line that is symmetrical.
Yes.
Okay. So, throughout this entire, last couple of examples, we've been talking about how sine is an odd function and cosine is an even function, right? So let's kind of describe what that actually looks like again, right? So for an odd function, right? So an odd function has the property where if you plug in a minus, you plug in a minus argument there, that minus sign kind of comes out in front, right? So if we take f of minus t, right, that equals to minus f of t, right? So plugging in a minus time will give you a minus function value, right? Now, what does this look like visually? So if we draw this visually, right? And I will take our previous example because our previous example was an odd function, right? Right, so this is the line f of t is equal to t, right? So if you took any negative t value, right? So let's say that we have f of t is right here, right? So let's say this is t some t naught right here, right? We get f of t naught, right? If you took the minus value of that, so let's say that you take minus t naught, which is this location here, right? If you actually measured and look at the actual value, you'll see that f of minus t naught has the same magnitude as f of t naught, just with a minus sign. Okay. Now, visually, the way you can kind of see this is that odd functions are symmetric across a diagonal line, right? And so if you were to draw a line, right, like this, right, basically a line that kind of bisects the origin and has kind of a a line. Essentially, this is the line f of t is equal to minus t, right? This function is symmetric across this line. Right, so essentially that symmetry line acts there is kind of like a mirror, right? And so if you look past in the mirror, you get the same image on both sides there. Right? Now the symmetry line for odd functions is a little bit hard to see, and so it's not always easy to kind of draw a diagonal line and look at that symmetry. Once you kind of see it a few times, you start to kind of see that pattern. You can see what it looks like, but it's not the easiest, right? So I would say if you're testing for an odd function, then I would say just go off that criteria right there. So plug in some values of minus t into your function, and then see if you get the minus function value that comes out. Right? Now for odd functions, right? Odd functions will always have 0 coefficients for a naught and a n. Because why is that, right? Because a0 and an, if you look back at our Fourier series expansion, right? A0 and an are the coefficients that correspond to the cosine part of the expansion, right? And we know, just because we've done it a lot, that cosine is an even function, right? And so it wouldn't make sense for the coefficients of an even function to be non-zero for an odd function, right? And so if you can tell right away that your function is odd, right? There's no reason to kind of go through the whole song and dance to compute a0 and an if they're going to be 0. Okay. So this is a simplification you can make on your homeworks, homework 5. If you can tell that your function is odd, then you don't even have to bother computing a0 an because they're going to be 0. Now you're welcome to, right? And so it's not it wouldn't be wrong to compute A0 and A. So if you're not sure, it wouldn't hurt to compute it. But if you can identify kind of beforehand that it's odd, then just you can save yourself some time and just set it equal to 0. Okay. This is definitely a skill. I would, some people would look at this and say like, this is kind of optional, and you can just say just compute everything anyway. But I will say this is a very useful skill to have for the second midterm because this will save you a lot of time on the second midterm. You can avoid computing half the coefficients, right? All right. Any questions on this? Yes.
Will it be pretty obvious?
It will be. Yeah. 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 I'm not going to give you a weird function where it's you have to kind of guess where it's even or odd. It should be pretty obvious if it's because even functions actually have a I would say it's easier to identify an even function than an odd function. So for even functions, right? So even functions have the characteristic where if you take the minus of the argument, you end up with the same thing as well, right? So the minus sign effectively gets kind of canceled out, okay? Now, I would say the most famous, or I would say the simplest even function that's out there is a quadratic function, right? So if you have f of t is equal to t squared, right? Right? That is our famous parabola function. Right? And so if you take, f of t naught, which is here, right? And you take f of minus t naught, which is here, right? Right, you can see just visually that they kind of give you the same value, right? Even functions are easier to identify because even functions are always symmetric across the vertical axis. Right? Okay. So your symmetry line is a line that's already present in your plot. Okay. All right, so remember the way to look at symmetry lines is just think of it like a mirror, right? And so you should see the same thing on both sides of the mirror. Okay. So for even functions, the opposite is true. So for even functions, the b ends are going to be 0. Okay. And so if you have a function that's even, then there's no reason to compute the coefficients for the bn coefficients. Okay, save yourself a little bit. Even functions are a little bit more work because you do have to compute a0, and so there are 2 expressions that you have to compute. But a0 usually is pretty straightforward to compute. So it's most of the work is going to be either an or. Okay. All right. Any questions? Any questions on that? Okay. All right. So last thing I want to cover before we leave for spring break is the idea of a half-range expansion. Okay. So a half-range expansion kind of takes this idea of an even and odd function and kind of expands on despite the name of half. Right? So for half-range expansions, we're usually looking at functions that are only defined for, let's say, half of a period. Right? So let's say that we have a function. So let's look at our quadratic again, actually. So let's say f of t is equal to t squared. Right? But let's say that this is only defined on the positive side of the t-axis, right? So it's only defined from 0 to L. right? And so we have a function that looks like that. All right. So since our function here is only defined for a half period, it's only defined on the positive t-axis, right? We can make assumptions in terms of what the function will look like on the other side. Right? Because on the one hand, we can assume that we have an even function, right? So an even function will kind of just look kind of like this, right? Right? Where remember we make our symmetry line equal to the positive y-axis, right? And so we just kind of keep continuing right there. Or, right, we can actually make the assumption that maybe our function is going to be an odd function, right? Where instead of kind of mirroring the same values as the positive, on the negative t-axis, we instead invert them and go the other way, right? Right. So let's say that instead we assume that we have an odd function, and our function just looks like that. Right. So depending on how we assume how the function looks like, right, that's going to affect how we compute the Fourier series coefficients, right? And so for any given function that's defined on a half period like this, we can create what's called the even half-range expansion or the odd half-range expansion. Okay. So the even half-range expansion, the way we do that is we only compute the Fourier series coefficients associated with the even functions, right? So that means we're only going to compute A0 and AN. Meanwhile, for the odd half-range expansion, right? For the odd half-range expansion, we're only going to compute the Fourier coefficients associated with the odd components of the Fourier, which is just Bn. So in some sense, you can say that we're forcing the function to have either an odd or an even character to it just by computing only those coefficients. Okay. And to kind of help save you some time, or it doesn't actually save you some time, but since the function is only defined from 0 to L, that does affect how we compute our coefficients as well. So we do modify our formulas here just because our function technically only defined from 0 to L. Okay. So instead of integrating over a full period, we're integrating just from 0 to L. And then we essentially multiply everything by 2. Okay. Okay, so our new expression for A0 is going to be 1 over L integral from 0 to L f of t dt, right? Our AN is going to be 2 over L integral from 0 to L of f of t cosine of n pi t divided by L dt. Right? So only difference between these expressions and the previous one is that we're only integrating from 0 to L, and we're multiplying everything by 2. Right? And then our Bn expression looks the same. So Bn is 2 divided by L, integral from 0 to L, f of t, sine of n pi t divided by L dt. Right? And by the way, these formulas here are not just limited to the half-range expansions. If you know you're ahead of time that your function is even or odd, you can use these expressions as so these formulas here, these modified formulas, they also work if your periodic function was even or odd.
For certain.
Exactly. So you can actually go back to the previous examples that we did and use these formulas and only integrate over the half period. You'll get the same. Okay. But you want to be careful. But so if your periodic function is neither even nor odd, that does happen. It is possible to have those. And you have to compute all 3 coefficients, and you have to use the original expression that we had before. Okay, so let's do one more example, and then we'll call it for today. Any questions on this before we jump into the last example? Okay, all right, so for the last example, let's compute an even half-range expansion, just because the last 2 examples we did were odd. Okay, so we're going to compute the even half-range expansion of f of t is equal to t squared. Okay. And let's do it from t is equal to from 0 to let's do 0 to 2. Actually. Okay. All right. So this is a half-range expansion, so that means we're going to continue we're going to continue this function from -2 to 0, right? And so that means our half period L is equal to 2 in this case. Okay. Okay, so for an even half-range expansion, we're just going to compute A0 and AN. So let's go ahead and plug in for those. Okay, so A0 is equal to 1 divided by 2 integral from 0 to 2 of t squared dt. All right, so we go ahead and plug in for that. So we integrate, we get 1 over 6 t cubed, evaluated from 0 to 2. Okay. Question? Yes.
You said that L is going to be 2?
Yes.
Because the previous L with the sawtooth was 2 over 2 each equals 1.
Right. So remember, but this is just a half here, right? So remember, for half range expansions, we're only defining it on the positive t-axis, right? Okay. So even though this function is only defined from 0 to 2, since we're computing a half range expansion, we're assuming that the full period goes from -2 to 2, right? And then just whatever's not there, we're kind of drawing in, we're kind of assuming what the function looks like from -2 to 0. Yeah. So, because we're doing a half range expansion for the negative values of t, we're making an assumption of what the function actually is. And so the half period L here is still 2, even though the function's only defined from 0 to 2. Good question. That is, it's a subtle point, but it is important. Okay, so let's go ahead and evaluate this integral. So we have basically 2 cubed divided by 6. So 2 cubed is 8. And so we have 8 over 6, which is 4 over 3. Finally, we have a problem here with a non-zero a naught, although we kind of forced it to be because we said that we're doing an even half range expansion. But for once we have a naught is equal to something other than 2. All right, and then let's do an. So an is equal to, we plug in for the formula, we get 2 over 2 integral from 0 to 2 t squared cosine of n pi t divided by 2 dt. All right. So we have once again another case of integration by parts, and so let's go ahead and do just that. All right, so I'm gonna do this by table actually, just because we can kind of do it all in kind of one step here. Okay. Okay. So let's go ahead and integrate this. So on the left-hand side, we have the t squared. So we're just going to take derivatives on that left-hand side. So we have t squared, 2t, 2, and then 0. Okay. And then on the right-hand side of the table, we have cosine of n pi t divided by 2. Okay. Okay, so we're going to take antiderivatives on that other side. So we have a 2 divided by n pi sine of n pi t divided by 2. Okay. All right, we take another integral. We get a minus 2 divided by n pi quantity squared cosine of n pi t divided by 2. Okay. And then we take another antiderivative. We get minus 2 divided by n pi cubed sine of n pi t divided by 2. Okay. And so let's just go diagonally down the table. So we take this term multiplied by that term, positive sign, this term multiplied by that term, minus sign, and then this term multiplied by that term, positive sign. Okay. Okay. All right, so let's go ahead and write this all out. So first term we have t squared multiplied by 2 divided by n pi sine of n pi t over 2. So that is 2t squared divided by n pi sine of n pi t divided by 2. Okay. Next, we have this quantity right here. So the minus signs are going to cancel out. So we have a minus sign that comes from the integration, a minus sign that comes from dv. And so it's going to be a plus. Okay. We have 2t times 2 squared. So that's going to be an 8t divided by quantity n pi squared. Okay. Cosine of n pi t divided by 2. And then last term here, we have 2 cubed, which is 8, multiplied by another 2 that comes from the left-hand side of the table. That gives us 16 divided by n pi quantity cubed sine of n pi t divided by 2. Okay, evaluated from 0 to 2. Just check my work real quick, make sure I didn't make any mistakes. Let's see. Okay, plus 2 squared. Okay, looks good to me. Okay. All right, so let's evaluate this at our integration bounds. And so we're going to plug in 2 and 0, right? So we plug in t is equal to 2. We get 2 times 2 squared, which is 2 cubed, which is 8. That's 8 over n pi sine of n pi t divided by 2. T is equal to 2, so that gives us sine of n pi. Okay. That's a great sign because we know sine of n pi is just going to be 0, so that's something that's going to cancel out. Plus 8t, so 8 times 2 is 16. 16 over n pi squared, cosine of n pi t divided by 2. T is 2, so 2 over 2 is 1. So that's cosine n pi minus 16 over n pi cubed sine of n pi t over 2. 2 over 2 is 1, so sine of n pi. With these Fourier problems, the integrals always look intimidating, but a lot of the terms do cancel out, which is good. Okay, and then we have everything evaluated at 0 as well. Okay, so the first two terms in our integral here are just going to be 0 because we have, 2 times t squared, which is 0, right? So we have 2 times 0 squared divided by n pi sine of 0 plus 8 times 0 divided by n pi squared cosine of 0 minus 16 over n pi cubed sine of 0. Okay. All right, and so we're in luck. Most 5 out of 6 of these terms are going to be 0, and so that's great. Okay. All right, so first, on the first set of parentheses, we have 2 terms with sine n pi. We already know that's going to be 0, so let's go ahead and cross these out. Okay, sine n pi equals 0 for all n that are integers or whole numbers. Okay. Okay. That's something we've seen in our previous 2 examples, right? We go down to the next set of parentheses here. We have this first term is equal to 0 because we have 2 times 0 squared, so that's going to be 0. And in fact, sine of 0 is also 0. So there's 3 zeros there. So that's going to be super 0, right? Next term here, that's also going to be 0 because we have 8 times 0 times cosine 0. So that 0 is going to cancel that out. Last term there, also 0 because sine of 0 is 0. Okay? So the only term here that survives is this term right here. So we have an is equal to 16 divided by n pi squared cosine of n. Okay. Which I forgot to do this on the previous example. Remember that cosine n pi is just minus 1 raised to the n power. And so the 16 divided by n pi squared times minus 1 raised to the n. Right? Good. All right, and then finally, let's just compute the first 3 terms here. Right, so we have A1, A2, A3. Okay. All right, so for A1 here, so let's plug in n is equal to 1, we get 16 divided by 1 squared times pi squared, which is just pi squared. Minus 1 raised to the 1 power is a minus sign, so we have a minus 16 over pi squared. Okay. Next, we have n is equal to 2. And so that's going to be 16 over 2 squared, which is 4. So that's going to be 4 over pi squared. Okay. Then we multiply that by minus 1 squared, which is just a positive 1. So that just ends up with a positive number 4 over pi squared. Okay. Lastly, for A3, we have 16 over 9 pi squared. And then we have a minus sign because minus 1 cubed is minus 1. Okay, and so finally we can write out the expansion for this. And so we have f of t is equal to, right? We can't forget a naught, right? So for your even functions, don't forget that you computed a naught here, right? So a naught for this problem was 4/3, okay? Minus 16 over pi squared, cosine of pi t divided by 2, okay? Plus 4 over pi squared, cosine of pi 2 pi t divided by 2, which is just, pi times t, minus 16 over 9 pi squared, cosine of 3 pi t divided by 2. Plus dot, dot, dot. All right, and so that's how you do an even half-range expansion. So you basically just assume what the function looks like on the other side. You only compute either the A coefficients or the B coefficients, depending on if you're doing an even or odd half-range expansion. But after that, the problem kind of proceeds in the same way. Okay. So Fourier, I would say Fourier is not too complicated. You're basically just doing the same method over and over again, just with kind of different applications. Just make sure that you can identify even and odd functions, and that kind of saves your life little bit for these points. Okay. Any questions? Yes.
And then will you be expecting us to put that into a series or articulate it in a form of summation?
You don't have to. I mean, that's already kind of implied when you have this we have this right here. So just writing out the first few terms and the expansion like that, that's fine. Any other questions? Okay, all right. So that's all the time we have for today. So thank you guys for coming today. I hope you guys have a good, restful spring break. And I will see you guys in almost 2 weeks. You too, Anthony.
Last time she was like, we looked at the slides if we needed to. I mean, I'm sure my name is now.
You too.